Welcome, everyone, to another session on Dr. Liu's VCE Physics channel. In this video, we'll thoroughly address the magnetic flux and Lenz's law questions from the NHT 2024 physics examination. I will guide you through the step-by-step solutions and the underlying concepts required to master these problems. Teachers, parents, and fellow students are encouraged to contribute any additional insights or corrections. When the switch of coil 1 is initially closed, a steady current flows. Opening the switch then causes this current to drop to zero. It is this change from a steady current to no current in coil 1 that generates a changing magnetic flux through the coils, which in turn produces a reading on the ammeter. Once the current is completely gone, the flux returns to a constant value, and the ammeter reading will revert to zero. Changing magnetic flux induces an EMF. The magnitude of this induced EMF is proportional to the rate of change of flux. Zero rate of flux change means zero EMF, maximum rate of flux change means maximum EMF. By Faraday's law, the induced EMF always acts to oppose the flux change. Thus, an increasing flux, positive rate, yields an opposing, negative, EMF. The approach of the magnet to the loop causes a change in magnetic flux through it. This changing flux, as dictated by Faraday's law, then induces a current within the loop. As the magnet moves to the right, the loop experiences an increasing magnetic flux directed to the right. According to Lenz's law, the induced current will generate an opposing magnetic flux, which in this case means an increasing flux to the left. Applying the right-hand grip rule, this requires an anticlockwise current. As the magnet's north pole moves right toward the loop, the induced EMF increases. It hits its maximum when the north pole is at the loop because the rate of change of magnetic flux is highest there. As the magnet continues moving inside the loop, this rate of change decreases, becoming zero at the loop's center, making the EMF momentarily zero. When the magnet keeps moving right, the rate of change of flux increases again, but its direction reverses. This makes the EMF negative, and its magnitude grows. The EMF reaches its maximum negative value when the south pole fully exits the loop. If the magnet keeps moving right, the rate of change of flux then diminishes, causing the EMF's magnitude to decrease while its direction remains negative until the magnet is far away. This 8-mark section on magnetic flux and Lenz's law is worth 6.2% of the total 130 marks. The questions are structured as follows. Multiple choice. 2 marks. Question 6 explains how a changing magnetic flux induces an electromotive force, EMF, in a coil. This concept is further illustrated in question 8, with a graph showing the variation of magnetic flux and the corresponding induced EMF over time. Short answer. 6 marks. Questions 6a and 6b focus on Lenz's law. This law states that the induced EMF always opposes the change in magnetic flux that caused it. The principle is applied to scenarios like a bar magnet moving through a wire loop. For question 6c, students are required to sketch a graph of the EMF generated in a loop as a function of time as a magnet moves through it. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.